In December 1937, the keel of a warship named Shikoku touched the ways at Yokosuka Naval Arsenal. 20 months later, in August 1941, she sailed into Tokyo Bay as a fully commissioned aircraft carrier capable of launching 63 combat aircraft into the Pacific sky. Across that same ocean, American shipyards were still laying the foundations of what would become the USS Essex, a vessel that would not see operational service for nearly 3 years after her keel was laid in April 1941. The paradox was inescapable. Japan, a nation with 1/13 the steel production of the United States, a country possessing fewer major shipyards and a fraction of America's industrial workforce, was building fleet carriers faster than the most powerful industrial economy on Earth. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. The disparity was not an illusion. It was mathematical fact, recorded in steel tonnage and construction logs that would later be scrutinized by naval historians searching for answers in the rubble of defeat. The Shikoku and her sister ship Zuikaku represented the pinnacle of Japanese carrier design in 1941, displacing 25,675-ton standard, measuring 257.5 meters in flight deck length, and capable of 34 knots powered by 160,000 shaft horsepower. Both were completed in less than 4 years from keel laying to commissioning. The Zuikaku, begun at Kawasaki's Kobe Yard in May 1938, joined the fleet in September 1941. Together, they formed the 5th Carrier Division and sailed to Pearl Harbor 3 months later as the most advanced carrier strike force the world had ever seen. Meanwhile, America's first Essex-class carrier, ordered under pre-war estimates with unlimited funding and access to the world's largest steel mills, would require 32 months from keel to commission, with her sisters averaging between 14 and 22 months depending on yard capacity and the chaos of wartime prioritization. The question haunted American naval planners throughout 1942 as they watched their carrier force struggle to replace battle losses while Japanese carriers appeared with disturbing regularity despite confirmed reports of Japan's limited industrial base. How was this possible? How could an island nation that imported 80% of its petroleum, 90% of its rubber, and 70% of its iron ore outpace the industrial colossus that would eventually crush it under the weight of its own production capacity? The answer lay not in superior technology or more efficient workers, but in decisions made 15 years before the first bomb fell on Pearl Harbor, in doctrines written by men who understood that Japan would never win a long war, and in the simple mathematics of choosing speed over durability, elegance over redundancy, and the short decisive battle over the grinding attrition that industrial warfare inevitably becomes. These choices were not mistakes in 1937. They were rational responses to irreconcilable strategic realities. Japan could not match American industrial output. Japanese planners knew this with the certainty of demographic and economic data that could not be argued away by nationalist rhetoric. Therefore, Japan must win quickly or not at all. Every aspect of Japanese naval construction from 1937 onward reflected this understanding, and nowhere was it more evident than in the carrier building program that produced Shikoku and Zuikaku. Japan's carrier program did not begin with Shikoku. It began in 1922 with the Washington Naval Treaty, a document that simultaneously constrained Japanese ambitions and liberated Japanese innovation. The treaty limited aircraft carrier tonnage to 81,000 tons for Japan versus 135,000 for Britain and America, a 5-to-3 ratio that Japanese naval officers regarded as an insult to national honor and a death sentence for Pacific defense. The ratio was mathematically precise and politically explosive. It reflected Western estimates of Japan's legitimate defensive needs while ensuring permanent Anglo-American naval superiority in every category that mattered. Japanese negotiators protested, argued, and ultimately accepted the terms because the alternative was a naval arms race that Japan's economy could not sustain and military confrontation that Japan's navy could not win. But the treaty also defined what a carrier was not, and in those gaps Japanese designers found room to create vessels that blurred the line between auxiliary and combatant, between experiment and weapon, between the permissible and the prohibited. The H-SHA, commissioned in 1922, was the world's first purpose-built aircraft carrier, displacing just 7,470 tons and measuring 168 meters overall length. She was not particularly fast at 25 knots, nor heavily armed with 14-centimeter guns and two 7.7mm machine guns, nor capable of launching more than 21 aircraft from her 168-meter flight deck. Her island superstructure was small, mounted on the port side in early configuration before being removed entirely in 1923 to improve flight operations. Her machinery consisted of two shafts driven by Parsons-geared turbines producing 30,000 shaft horsepower, adequate but not impressive. She carried a crew of 550 officers and men who pioneered Japanese naval aviation techniques that would mature into the most sophisticated carrier doctrine in the world by 1941. But she was operational 5 years before Britain's Hermes and 7 years before America's Ranger, and she taught Japanese naval aviators lessons about deck operations, arresting gear, and coordinated strikes that would prove invaluable when war came. More importantly, she established the institutional framework within which Japanese carrier aviation would develop, specialized training schools for carrier pilots, maintenance procedures for shipboard aircraft, tactical doctrines for multi-carrier operations, and the organizational culture that valued aggressive offense over defensive caution. The treaty's real gift to Japan was the conversion clause permitting existing capital ship hulls to be completed as carriers. 2 battle cruisers under construction, Akagi and Kaga, were permitted to be completed as carriers to fill out Japan's permitted tonnage without requiring new construction that would consume limited shipyard capacity and national budget. Akagi emerged from Kure Naval Arsenal in 1927 as a 36,500-ton hybrid with 3 flight decks arranged in a distinctive stepped configuration, the upper deck 190 meters long, the middle deck 15 meters shorter, and the lower deck used primarily for aircraft storage. She mounted 10 20-centimeter guns in casemates along her hull, 6 single 12-centimeter anti-aircraft guns, and 22 25mm machine guns in various mounts. Her most distinctive feature was the downward curved smokestack that vented exhaust beneath the flight deck, an engineering compromise intended to keep smoke off the landing area but creating heat and turbulence problems that would require modification in 1935. 8 boilers fed for turbines producing 131,200 shaft horsepower for a maximum speed of 31 knots, adequate for fleet operations but slower than the carriers Japan would build later. She carried 60 aircraft operationally with room for more in reserve, and her crew numbered 1,600 officers and men. Kaga followed from Yokosuka Naval Arsenal in 1928 at 38,200 tons with similar 3-deck configuration, converted from a Tosa-class battleship hull after the original Kaga battle cruiser hull was destroyed in the 1923 Great Kant earthquake. She mounted 10 20-centimeter guns, 16 12-centimeter guns, and 22 25mm guns, heavier armament than Akagi reflecting her battleship origins. 8 boilers produced 91,000 shaft horsepower for just 28 knots maximum speed, the slowest of Japan's large carriers and a limitation that would become critical in coordinated multi-carrier operations. Her flight deck configuration was modified in 1935 to a 2-deck system eliminating the lower flight deck, and her funnels were reconfigured to vent downward like Akagi's. She carried 90 aircraft, more than any carrier in the world when commissioned, though operational loads rarely exceeded 70 due to deck handling constraints. Both were large, well protected with armor belts up to 152mm and deck armor up to 76mm over magazines and machinery, and slow by later standards but adequate for the battle line tactics that still dominated naval thinking in the 1920s. They were not efficient carriers by the measure of aircraft-to-tonnage ratio, carrying fewer aircraft per ton than purpose-built designs would achieve, but they were in service, training crews, and developing doctrine while American and British carriers remained drawings on paper or hulls slowly taking shape in peacetime yards operating on peacetime budgets with peacetime urgency. The experience gained operating these ships was invaluable and irreplaceable. Japanese carrier crews learned how to launch coordinated strikes involving dozens of aircraft, how to recover damaged planes on pitching decks in rough seas, how to rearm and refuel aircraft while maintaining continuous combat air patrol, and how to coordinate fighter defense against attacking bombers. These skills could not be taught in classrooms or learned from manuals. They required years of practice at sea, and Japan's early start provided that practice while potential enemies were still debating carrier design philosophy. By the mid-1930s, Japan possessed a carrier force of 4 ships, 8 sha, Akagi, Kaga, and the light carrier RYJ, completed in 1933 at 10,600 tons displacement. American carrier strength stood at 3 E. Langley, converted from the collier Jupiter in 1922 but already obsolete by 1935, Lexington and Saratoga, converted battle cruisers commissioned in 1927 at 36,000 tons displacement each, similar to Japan's conversions but heavier, faster at 34 knots, and carrying more aircraft. Britain operated 7 carriers including the old Argus, converted from a liner in 1918, Hermes commissioned in 1924, the fleet carriers Furious, Glorious, and Courageous converted from large light cruisers, and Eagle and Ark Royal. The numerical balance slightly favored the Allies, but operational readiness and crew experience heavily favored Japan. Japanese carrier pilots trained constantly in the inland sea and off the Chinese coast during operations related to Japan's expanding war in China. Their exercises were brutal in demands and realistic in simulated combat, with pilots expected to launch in weather conditions that would ground Western aviators, land on decks in sea states that would scrub Western operations, and navigate at night without radio aids. Casualty rates in training were high, but survivors were superbly qualified. By 1936, when Japan withdrew from the treaty system and began unrestricted naval construction, the combined fleet possessed institutional knowledge of carrier warfare that no other navy could match. The withdrawal was not sudden or unexpected. Japan had signaled intent to withdraw years earlier, citing the refusal of Western powers to grant parity in capital ships and the refusal to acknowledge Japan's defensive requirements in the Western Pacific. The treaty would expire in December 1936, and Japan announced it would not renew or negotiate extensions. The announcement freed Japanese naval architects from tonnage restrictions and allowed design of the carriers that Japanese doctrine required rather than the carriers' treaty limits permitted. The decision to build Shikoku and Zuikaku came in 1937 under the Third Replenishment Program, a construction plan that prioritized carriers over battleships for the first time in Japanese naval history. The shift reflected changing operational doctrine influenced by experience in China, where carrier-based aircraft had proven far more effective than coast bombardment by battleships in supporting amphibious operations. The combined fleet's most influential officers, including Admiral Isoroku Yamamoto, who would later plan the Pearl Harbor attack, argued that the decisive battle would be won by air power, not by battleship gunnery, that carriers, not battleships, should receive construction priority, and that Japan needed at minimum 6 fleet carriers in 2 divisions of 3 ships each to execute the massed carrier strikes doctrine then being developed. The design brief was clear: build a fleet carrier optimized for offensive operations, capable of long-range strikes against enemy bases and fleet concentrations, able to absorb punishment from enemy counterattacks, and ready for rapid construction using proven technologies and existing shipyard infrastructure without requiring development of new systems that might delay completion. The result was a ship that measured 257.5 meters in overall length with a beam of 26 meters at the waterline widening to 29 meters at flight deck level, and a draft of 8.87 meters fully loaded. Standard displacement was set at 25,675 tons, well within the capacity of Japan's largest building ways at Yokosuka and Kure, which could handle ships up to 40,000 tons. The flight deck measured 242.2 meters long and 29 meters wide, featuring 2 aircraft elevators positioned on the center line, 1 forward of the island superstructure and 1 aft, each capable of lifting aircraft weighing up to 5 tons. At rates approaching 1 per minute. Hangar space was divided into 2 levels with sufficient room for 72 aircraft in theory stowed wingtip to wingtip, though operational loads rarely exceeded 63 due to maintenance requirements and deck parking of ready aircraft. The island superstructure was mounted on the starboard side, a departure from some earlier Japanese carriers that experimented with portside islands, and integrated the bridge, flight control positions, and funnel into a compact structure that minimized disruption to flight operations while providing excellent visibility for the air operations officer who controlled all launches and recoveries. Armament was specified to provide both anti-aircraft defense and limited surface capability. 16 12.7 cm dual-purpose guns were mounted in 8 twin turrets, 4 on each beam, positioned to provide overlapping fields of fire against attacking aircraft or surface targets. These guns could fire 16-kilogram shells to an effective range of 14,700 meters at surface targets or 9,400 meters against aircraft, using mechanical fire control computers that predicted target position based on observed speed and bearing. 36 25mm Type 96 anti-aircraft guns were installed in 12 triple mounts distributed around the flight deck edges and island structure, providing close-in defense against dive bombers and torpedo aircraft that penetrated the medium-range 12.7 cm battery. Additional machine guns and small arms were provided for defense against strafing attacks and for arming damage control parties. The armament suite was lighter than comparable American carriers that mounted 12 5-inch guns plus dozens of 40mm and 20mm weapons, reflecting Japanese confidence in fighter defense and offensive doctrine that emphasized destroying enemy carriers before they could launch rather than defending against enemy strikes after launch. Armor protection was concentrated around vital spaces using weight saved from reduced armament and simplified internal systems. The flight deck incorporated 46mm armor plate over the magazines and machinery spaces, sufficient to defeat shells from destroyer-caliber weapons and provide fragmentation protection against bomb near misses but inadequate against direct hits from armor-piercing bombs dropped from high altitude. The belt armor measured 165mm at its thickest point, protecting the machinery spaces and magazines below the waterline, tapering to 75mm at the upper edge. Horizontal deck armor consisted of 150mm plates over the magazines where a single penetrating hit could detonate stored munitions and destroy the ship, and 100mm armor over machinery spaces where flooding or fire could disable propulsion. Underwater protection featured a complex system of fuel tanks, void spaces, and torpedo bulges designed to absorb torpedo detonations and isolate flooding from spreading to vital compartments. This protection scheme was tested in combat simulations and judged adequate against single torpedo or bomb hits but vulnerable to multiple simultaneous impacts that could overwhelm damage control capacity. The machinery plant consisted of 8 Kampen boilers arranged in 4 fire rooms, each fire room containing 2 boilers and separated from adjacent spaces by armored bulkheads to prevent a single penetrating hit from disabling multiple boilers. The boilers produce superheated steam at 300 pounds per square inch and 400 degrees Celsius, fed to 4 Kampen geared turbine sets, each driving a single propeller shaft. Total output was rated at 160,000 shaft horsepower at maximum power settings, sufficient to drive the ship to 34.2 knots in trial conditions with clean hull and calm seas. Operational speed was typically 32 knots sustained, and maximum range was 9,700 nautical miles at economical cruising speed of 18 knots, extending to 6,300 miles at 25 knots and just 3,200 miles at maximum speed. 4 propeller shafts were fitted, each turning a 3-bladed bronze propeller 4.2 meters in diameter. The shafts passed through the hull via sealed glands that permitted rotation while preventing water ingress, a technology Japanese yards had perfected through decades of destroyer and cruiser construction. Fuel capacity was critical for extended Pacific operations. Internal tankage held 5,000 tons of heavy fuel oil for the boilers, sufficient for the rated range at cruising speed but requiring replenishment from fleet oilers for extended operations. Aviation gasoline storage totaled 496 tons in armored tanks positioned deep in the hull away from potential bomb or torpedo hits, enough to refuel the embarked air group approximately 8 times before replenishment was required. Fresh water for crew use and boiler makeup was produced by distillation plants capable of generating 150 tons per day, supplemented by storage tanks holding an additional 400 tons. The crew of 1,660 officers and men consumed approximately 60 tons of fresh water daily for drinking, cooking, washing, and laundry, requiring continuous distillation during extended operations. The construction process reflected decades of accumulated experience building capital ships under tight weight and budget constraints. Yokosuka Naval Arsenal, where Shikoku was built, had been constructing major warships since the 1880s when the Meiji government established it as one of 4 primary naval shipyards serving the Imperial Japanese Navy. The yard possessed 6 building ways capable of handling ships up to 30,000 tons on the largest way and smaller vessels on the others, for dry docks including one able to accommodate the Yamato-class super battleships then under construction, and complete fabrication facilities for all major ship components. The yard produced its own armor plate using electric arc furnaces and rolling mills that could fabricate plates up to 450 mm thick for battleship turrets, though carrier armor required only modest thicknesses. Turbine and boiler shops manufactured propulsion machinery to designs developed by Campen, the Naval Technical Bureau, using patterns and tooling standardized across multiple ship classes to reduce cost and construction time. Electrical shops wound generators and motors, fabricated switchboards and distribution panels, and assembled the miles of cable required to power lighting, ventilation, elevators, radios, and the hundreds of electrical systems aboard a modern warship. By 1940, Yokosuka employed nearly 40,000 workers including skilled tradesmen, engineers, laborious, and administrative staff. The workforce was entirely male, reflecting Japanese cultural norms that excluded women from heavy industrial work, and predominantly Japanese with small numbers of Korean laborious in unskilled positions. Workers were organized into specialized trades under master craftsmen who had learned their skills through apprenticeships lasting a decade or more. Welders, riveters, pipefitters, electricians, machinists, and dozens of other specialties worked in coordinated teams supervised by yard foremen who reported to section chiefs responsible for specific ship systems or construction phases. The hierarchy was rigid, discipline strict, and quality control enforced through inspection at every stage rather than statistical sampling methods Western yards would adopt later. The yard operated on principles of modularity and prefabrication that would not become standard in Western shipbuilding until the emergency programs of 1942 forced rapid adoption to meet production quotas. Hull sections were fabricated in shops away from the building way where weather and cramped conditions would slow work, then transported by crane to the way for assembly. This allowed multiple sections to be worked simultaneously by different crews, with armor plate fitted, piping installed, and equipment mounted while the section was accessible on all sides in the shop rather than after installation when access was limited. Welding was used for non-critical joins and interior structure where weight savings justified the technique, but riveting remained standard for primary hull structure and armored elements where proven reliability outweighed weight considerations. A typical carrier hull required approximately 3 million rivets driven by teams of riveters working in shifts around the clock during peak construction phases. The keel of Shikoku was laid on the 12th of December, 1937 in a ceremony attended by Navy officials, yard managers, and Shinto priests who blessed the ship and performed rituals intended to ensure successful construction and safe service. The keel consisted of longitudinal steel girders forming the backbone of the hull, laid on massive wooden blocks arranged on the building way at precise intervals calculated to support the growing weight as construction progressed. The blocks were positioned with millimeter accuracy using surveying instruments, and their height was adjustable via wedges allowing the hull to be raised or lowered as needed during construction. The building way sloped gently toward the water to facilitate launching when construction reached the point where the hull could float. Construction proceeded in phases that minimized bottlenecks and maximized parallel work streams. The first phase involved building the bottom hull from keel to turn of bilge, consisting of transverse frames spaced at regular intervals, longitudinal stringers connecting the frames, and hull plating riveted to the frame structure. Armor belt sections were fitted during this phase while access was good, with 165 mm plates heated to red heat for forming then riveted or bolted to backing structure. The double bottom was constructed with inner and outer hull plates separated by frames and bulkheads, creating compartments used for fuel oil storage, fresh water, or left void for damage protection. Approximately 400 watertight compartments were created by transverse and longitudinal bulkheads, each accessible via watertight doors or hatches that could be dogged shut from inside or controlled remotely from damage control stations. The second phase added the sides and deck structures, transforming the flat bottom into a recognizable ship hull. Transverse frames extended upward from the turn of bilge, following the calculated hull curvature that minimized drag while providing necessary volume for machinery, magazines, and habitability. The frames were fabricated in the metalworking shop from steel plates and angles, transported to the way, and lifted into position by massive cranes capable of hoisting 20 tons. Once positioned, they were temporarily braced while hull plating was fitted and riveted or welded into place. The side plating continued the armor belt upward to the main deck level, though belt thickness decreased from 165 mm to 75 mm at the upper edge where protection against underwater hits was unnecessary. The third phase involved machinery installation, a complex operation requiring precise timing and coordination. The 8 boilers were manufactured in the boiler shop, each weighing approximately 50 tons empty and measuring 4 meters high, 3 meters wide, and 6 meters long. They were transported to the building way and lowered through openings in the main deck that would later be sealed, positioned in their designated fire rooms on foundations bolted to the inner bottom, and connected via massive steam pipes to the turbines. The 4 turbine sets were even heavier, each weighing 100 tons and standing 2 deck heights tall. They were installed similarly through deck openings using the yard's largest cranes, positioned with millimeter precision over their foundations, and bolted down with dozens of foundation bolts torqued to precise specifications. The propeller shafts, each weighing 30 tons and measuring over 100 meters long for the outboard shafts, were inserted through stern tubes from outside the hull, aligned with turbine output flanges inside the ship, and secured with massive couplings. Installation proceeded while hull sections were still being joined, a parallel workflow that saved months compared to sequential construction where machinery installation would wait until the hull was complete. The risk was that design changes or construction errors might require removing installed machinery to correct problems, but Japanese yards had sufficient experience to minimize such occurrences through careful planning and skilled execution. Electrical generators were installed in dedicated compartments, each driven by steam turbines fed from the main boilers, providing electrical power for lighting, ventilation, pumps, elevators, and the increasingly complex electrical systems modern warships required. Distribution panels were mounted in protected spaces below the armored deck, and cable runs were laid through dedicated trunks that allowed maintenance access and fire protection. The 4th phase added superstructure, flight deck, and armament. The hangar deck was constructed as the main strength deck, a continuous steel structure from bow to stern that carried flight deck loads and provided primary longitudinal strength. It measured 196 meters long, 23 meters wide, and 5.2 meters high to overhead, sufficient for most carrier aircraft of the period though increasingly tight as aircraft size grew. 2 hangar levels were provided, stacked vertically, with the upper hangar opening directly onto the flight deck via the elevators and the lower hangar used for maintenance and storage. The flight deck structure consisted of steel beams supported by the hangar deck below and covered by 25 mm steel plating over most areas, increasing to 46 mm armored plating over magazines and machinery. The entire flight deck assembly was prefabricated in sections, lifted into place by crane, and welded or bolted to the hangar deck structure. The island superstructure was built as a separate assembly in the structural shop, a multi-level steel framework measuring 12 meters wide, 8 meters deep, and 20 meters tall, containing the bridge, chart room, air operations office, radio rooms, flag bridge, and numerous other spaces required for command and control. The funnel was integrated into the island, a complex ducting system that collected exhaust from all 8 boilers and vented it through a single uptake angled outboard at 26 degrees to keep smoke away from the flight deck. The entire island assembly weighed approximately 400 tons and was lifted onto the flight deck in a single operation requiring careful coordination of multiple cranes and guy wires. Armament installation involved mounting the 8 twin 12.7 cm turrets in spans projecting from the hull sides, 4 on each beam, positioned to provide unobstructed firing arcs across broad sectors. Each turret weighed 20 tons loaded and required power systems for training and elevation, ammunition hoists from magazines 2 decks below, and fire control connections to the central fire control position in the island. The 36 25mm guns in triple mounts were distributed around the flight deck edge and atop the island, each mount manually operated but directed by lookouts and fire control officers using optical sights. Additional equipment included searchlights for night operations, signal lamps for communications, boat cranes for handling the ship's boats, and anchors weighing 5 tons each with anchor chains consisting of links weighing 20 kilograms each. Aircraft support facilities were extensive and sophisticated. 2 catapults were installed on the flight deck forward, each capable of accelerating a 5-ton aircraft to 110 km per hour in 15 meters of travel, sufficient for takeoff when deck wind was inadequate for rolling takeoff. 9 arresting wires stretched across the aft flight deck, each capable of stopping a 5-ton aircraft landing at 130 km per hour within 50 meters. The wires were connected to hydraulic cylinders that absorbed landing impact, paid out at controlled rates as the aircraft decelerated, then retracted the wires for the next landing. Crash barriers were positioned forward of the arresting wires to prevent aircraft that missed all wires from striking aircraft parked forward. Fueling stations were distributed around the hangar deck with hoses that could pump 300 liters of aviation gasoline per minute, allowing rapid refueling of entire strike groups. Weapons elevators brought bombs, torpedoes, and machine gun ammunition from magazines to hangar and flight deck levels where ordnance crews armed aircraft under supervision of aviation ordnance officers. Shikoku was launched on the 1st of June, 1939, just 17 months after her keel was laid, in a ceremony that marked transition from construction to fitting out. The launching involved carefully calculated removal of the wooden block supporting the hull, replacement with greased launching ways, and release of restraining triggers that allowed the hull to slide stern first down the ways into the water. The ship was held by drag chains that controlled descent speed and brought the hull to a stop when fully afloat. Tugboats immediately took position alongside to prevent the hull from drifting in the current. And the ship was towed to a fitting-out pier where the next 14 months would be spent completing systems, testing machinery, and transforming a floating hull into an operational warship. Fitting out was as complex as initial construction and required different skills. With the hull afloat, large cranes could no longer be used, requiring shipyard workers to move equipment using the ship's own cranes and elevators. Boilers were lit for the first time to test steam systems and identify leaks in piping and valves. Turbines were slowly rotated by hand to check for binding or misalignment, then brought up to speed under steam while engineers monitored bearing temperatures and vibration. Propeller shafts were turned while observers checked for excessive vibration or seal leakage. Electrical systems were energized panel by panel, with technicians using voltmeters and ammeters to verify proper voltage and current distribution. Fire suppression systems were tested by actually flooding compartments and verifying pumps could remove water faster than it entered. Damage control parties practiced plugging simulated holes in the hull using wooden plugs, mattresses, and portable pumps. The flight deck received intensive testing with weighted sleds simulating aircraft to verify arresting gear could stop them safely. Catapults were fired hundreds of times with progressively heavier loads to ensure mechanical components could withstand repeated stress. Elevators were cycled up and down while loaded beyond their rated capacity to test safety factors built into the design. Ammunition hoists were operated for hours continuously to verify they could sustain combat firing rates without jamming. Radio equipment was installed and tested for range and clarity. Radar was not installed initially, as Japanese radar development lagged Western programs, but antennas and cabling were provided for future installation when equipment became available. The crew began reporting aboard in early 1941, initially small numbers of senior officers and petty officers who would form the ship's leadership, followed by ratings who would operate and maintain equipment. Training focused on learning the ship's layout, operating shipboard systems, and coordinating the hundreds of individual tasks required to get underway, launch aircraft, recover aircraft, and fight the ship in combat. Damage control drills were conducted weekly then daily as commissioning approached, with crews practicing fire fighting, flooding control, and casualty response under conditions simulating battle damage. Aircraft handling crews drilled moving aircraft from hangar to flight deck, spotting them for launch, and striking them below after recovery, timing themselves to achieve the speed required for sustained combat operations. She was commissioned on the 8th of August, 1941, exactly 44 months after construction began, in a formal ceremony transferring the ship from the shipyard to the Imperial Japanese Navy. The ceremony was attended by naval officials, government ministers, yard workers who had built her, and crew who would serve aboard her. The rising sun flag was raised for the first time at the stern, symbolizing the ship's transition from inanimate construction to living warship. The commanding officer read his orders assigning him command, accepted the ship from the yard superintendent, and took charge of all personnel and operations aboard. Within hours the ship got underway for shakedown training in the inland sea where the next 3 months would be spent identifying and correcting deficiencies in equipment, procedures, and training. Zuikaku followed an almost identical timeline, beginning at Kawasaki's Kobe shipyard where construction paralleled Shikoku's with constant communication between yards to share lessons learned and coordinate design changes. Keel laid the 25th of May, 1938. Launched the 27th of November, 1939 after 18 months of construction. Commissioned the 25th of September, 1941 after 40 months total. The ship's systems were identical to Shikoku's, ensuring parts compatibility and maintenance procedures could be standardized across both ships, simplifying logistics and training. Both ships joined the 5th Carrier Division under Rear Admiral C.H. Ichihara and immediately began intensive training in the inland sea, where they practiced launching coordinated strikes with other carriers, defending against simulated air attacks, and operating in rough weather conditions common in the North Pacific where combat would occur. By November 1941, they were considered combat-ready, their air groups proficient in level bombing, dive bombing, torpedo attack, and fighter interception. Each carried 18 Mitsubishi A6M20 fighters providing air defense and escort, 27 HED-3A1 Val dive bombers for attacking ships and shore targets, and 27 Nakajima B5N2 Kate torpedo bombers for anti-ship strikes, a balanced package capable of overwhelming any target within 200 miles and returning safely to the carrier. The United States began its own pre-war carrier construction program in 1939, after years of Depression-era budget constraints that limited naval expansion to replacement tonnage for obsolete ships and minimal new construction. The Naval Act of 1938 authorized construction of the first 2 Essex-class carriers, with additional units approved in 1940 as war in Europe demonstrated the importance of air power in modern naval warfare. The design evolved from the Yorktown class commissioned in 1937, incorporating lessons from that design while adding improvements suggested by exercises and war game analysis. The Essex class was designed to be larger, faster, more heavily armed, better protected, and capable of operating more aircraft than any previous American carrier, creating a vessel that could dominate sea areas through overwhelming air power rather than relying on battleship support. The design was ambitious, 27,100 tons standard displacement, increasing to 36,380 tons fully loaded with fuel, ammunition, aircraft, and provisions for extended operations. Overall length reached 270.7 meters with beam of 28.9 meters at the waterline, expanding to 45 meters at the flight deck edge including overhanging spans. Draft was 8.8 meters loaded, restricting access to some shallow harbors but providing excellent seakeeping in heavy weather. The flight deck measured 262 meters long and 29 meters wide, slightly longer but similar width to Shikoku, with 3 aircraft elevators including 2 centerline elevators and 1 deck edge elevator on the port side aft, an innovation that reduced vulnerability since damage to the deck edge elevator would not penetrate into the hangar and create flooding or fire risks. Aircraft capacity was rated at 91 aircraft in theory, with 36 fighters, 36 dive bombers, and 18 torpedo bombers, though operational loads typically numbered 80 aircraft, with remaining capacity used for spares and reserve aircraft. Hangar deck measured 196 meters long, 21 meters wide, and 5.3 meters high, comparable to Japanese designs but arranged in a single level rather than stacked multiple levels, providing better aircraft access and simpler damage control at the cost of reduced total capacity. Armament was far heavier than Shikoku, reflecting American doctrine that carriers must defend themselves against air attack rather than relying solely on fighter cover. 12 5-inch 38 caliber dual-purpose guns were mounted in 4 twin turrets and 4 single mounts, capable of firing 25 kilogram shells to effective range of 16,000 meters against surface targets or 11,000 meters against aircraft at rates up to 15 rounds per minute per barrel. These guns were controlled by Mark 37 fire control systems using radar to track targets and mechanical computers to calculate firing solutions, giving American carriers significant advantage in night combat and poor visibility conditions where Japanese optical systems were ineffective. Close-in anti-aircraft defense initially consisted of lighter weapons but was constantly upgraded as combat experience demonstrated heavier batteries were essential for survival. By 1943, standard armament included 44 40mm Bofors guns in 11 quad mounts distributed around the flight deck edge and island structure, plus 52 20mm Oerlikon cannons in single mounts providing last-ditch defense against aircraft that penetrated the 5-inch and 40mm batteries. The Bofors fired 900-gram shells at 120 rounds per minute to effective range of 3,600 meters, while the Oerlikons fired 120-gram shells at 450 rounds per minute to 1,500 meters, creating devastating firepower concentration that could destroy attacking aircraft before they reached bomb or torpedo release points. This armament weight required approximately 1,800 tons of displacement compared to roughly 800 tons for Shikoku's lighter battery, illustrating American willingness to trade aircraft capacity for defensive capability. Protection was similarly comprehensive, reflecting lessons from war games and intelligence reports suggesting Japanese torpedoes and bombs were more powerful than American weapons. Belt armor reached 102 mm at maximum thickness, protecting machinery and magazines, thinner than Shikoku's 165 mm belt but covering larger area of the hull. Deck armor was distributed across multiple levels rather than concentrated in single armored deck, with 38 mm weather deck, 38 mm second deck over machinery, and 64 mm third deck over magazines, providing better protection against bombs that could penetrate one deck but would be stopped by subsequent decks below. Underwater protection featured elaborate torpedo defense system with multiple compartments designed to absorb detonation energy and prevent flooding from spreading to vital spaces. This system was tested extensively using sections of hull subjected to actual torpedo detonations, and analysis suggested the ship could survive 2 or 3 torpedo hits without sinking, compared to Japanese carriers designed to withstand perhaps one hit before losing buoyancy or propulsion. The machinery plant consisted of 8 Babcock and Wilcox boilers producing superheated steam at 600 pounds per square inch and 450 degrees Celsius, higher pressure and temperature than Japanese boilers, and requiring more sophisticated metallurgy but providing better fuel efficiency. The boilers were arranged in 4 fire rooms separated by armored bulkheads, each fire room containing 2 boilers and capable of operating independently if adjacent spaces were destroyed. Steam fed for Westinghouse geared turbine sets producing 150,000 shaft horsepower total, slightly less than Shikoku's 160,000 horsepower but achieved with lower steam consumption due to higher inlet pressure and temperature. For propeller shafts drove bronze propellers 4.9 meters in diameter, larger than Shikoku's 4.2 meter propellers to absorb available power at lower rotational speeds, reducing cavitation and mechanical stress on shafts and bearings. Maximum speed was rated at 33 knots in trial conditions, 1 knot slower than Shikoku but achieved at lower power setting due to superior hull form and larger propellers. More importantly, the Essex class maintained higher sustained speeds in combat conditions where hull fouling, heavy loading, and rough seas reduced maximum speed for all ships. Range was 11,000 nautical miles at 15 knots, extending to 6,500 miles at 25 knots, providing excellent endurance for extended Pacific operations. Fuel capacity totaled 6,330 tons of Navy special fuel oil, heavier bunker than commercial vessels used but necessary for high-power operations and long storage without degradation. Aviation gasoline capacity reached 900 tons, nearly double Shikoku's 496 tons, reflecting larger air group and American doctrine emphasizing sustained operations rather than single overwhelming strikes followed by withdrawal. The construction process at American yards differed fundamentally from Japanese methods, reflecting different industrial organization and labor practices. Newport News Shipbuilding, where USS Essex was built, was a private commercial yard owned by the Newport News Shipbuilding and Dry Dock Company, operating under contracts with the United States Navy rather than as a government facility like Yokosuka Arsenal. The yard employed approximately 31,000 workers in 1941, comparable to Yokosuka but organized differently. Labor was civilian, unionized, and subject to collective bargaining agreements that specified work hours, overtime pay, safety requirements, and dispute resolution procedures. Workers could and did strike when contract negotiations failed, halting construction for days or weeks despite government pressure to maintain production. This created uncertainty in schedules and costs that Japanese naval arsenals never experienced, though American workers were generally more skilled and productive on a per-person basis due to higher education levels and better equipment. The yard operated 12 building ways capable of handling ships from destroyers to battleships, 3 large dry docks, and complete fabrication facilities for hull construction, machinery manufacture, and electrical systems. Unlike Japanese yards that produced armor plate and turbines in-house, Newport News purchased major components from specialized suppliers, armor plate from Carnegie Illinois Steel or Bethlehem Steel, turbines from Westinghouse or General Electric, boilers from Babcock and Wilcox or Foster Wheeler, and hundreds of other items from subcontractors across the country. This distributed production system was more efficient economically but created supply chain vulnerabilities when subcontractors face strikes, material shortages, or priority conflicts between competing government contracts. Japanese yards experience similar problems on smaller scale but maintain tighter control through vertical integration and government ownership. USS Essex had her keel laid on the 28th of April, 1941 in a ceremony that was functional rather than ceremonial, reflecting American pragmatism versus Japanese formality. The keel consisted of massive longitudinal girders positioned on the building way and secured to concrete foundations, providing the backbone onto which transverse frames and hull plating would be added. Construction proceeded using methods similar to Japanese techniques but with greater emphasis on welding over riveting. American yards had adopted electric arc welding extensively during the 1930s, and Essex's hull was approximately 60% welded compared to Shikoku's perhaps 30% welded. Welding was faster than riveting, required fewer workers, produced lighter structure for equal strength, and eliminated rivet holes that could leak. But welding required carefully controlled procedures, skilled welders holding certification from the American Bureau of Shipping or Navy inspectors, and extensive testing using X-ray and ultrasonic inspection to detect flaws invisible to visual inspection. Hull construction advanced rapidly during summer 1941, slowing somewhat after Pearl Harbor when the yard received orders to accelerate battleship repairs and destroyer construction simultaneously with carrier building. The yard was crowded with ships at various construction stages, repair ships damaged in Pacific combat, and merchant vessels requiring modification for military service. Cranes queued to lift components, workers competed for access to hull sections, and managers struggled to coordinate schedules across multiple high-priority programs. Despite these challenges, Essex's hull was structurally complete by April 1942, approximately 12 months after keel laying, comparable to Japanese timelines. Machinery installation followed, with boilers and turbines provided by subcontractors delivered to the yard and installed using the same techniques Japanese yards employed. The ship was launched on the 31st of July, 1942, 15 months after her keel was laid, in a ceremony attended by thousands of workers and government officials celebrating America's industrial response to Pearl Harbor. Fitting out consumed the next 5 months, during which the hull received armament, electronics, aircraft handling equipment, and the countless systems required for operation. Combat experience from Coral Sea and Midway influenced design changes implemented during fitting out, including heavier anti-aircraft armament, improved radar, better damage control systems, and modifications to aviation fuel systems that reduced fire risk. These changes delayed commissioning but produced a more capable ship. Essex was commissioned on the 31st of December, 1942, 32 months from keel laying to commissioning, 12 months less than Shikoku but achieved during wartime emergency conditions with unlimited budget and workforce, compared to Shikoku built during peacetime with normal budget constraints and workforce limitations. The comparison was not quite fair because contexts differed so dramatically, but the basic fact remained that American yards required nearly 3 years to build their first modern carrier while Japanese yards had completed 2 modern carriers in similar timeframe 5 years earlier. More telling than the first ship's construction time was the production rate for subsequent ships. Essex was followed by 14 more Essex-class carriers commissioned by war's end plus 9 more completed in the late 1940s, demonstrating the scalability of American shipbuilding when fully mobilized. USS Yorktown CV-10, the second ship of the class, required just 16.5 months from keel laying on the 1st of December, 1941 to commissioning on the 15th of April, 1943. USS Intrepid required 17 months. USS Hornet CV-12 required 15.5 months. USS Wasp required 18 months. USS Franklin required 15 months. Every subsequent ship commissioned faster than Essex as yards refined procedures, workers gained experience, and suppliers eliminated bottlenecks. By 1943, American shipyards were completing an Essex-class carrier every 2 months on average, a production rate Japan could never approach even theoretically given its limited industrial capacity and resource base. 9 Essex-class carriers were commissioned in 1943 alone, more carriers than Japan had built in the previous decade. The disparity reflected fundamental differences in industrial capacity, resources, and strategic depth. Japan began the Pacific War with 6 fleet carriers operational and sufficient industrial capacity to build perhaps 20 more given unlimited time and resources that in reality were not available. America began with 7 fleet carriers and industrial capacity to build hundreds if required and resources were available. Japanese steel production in 1941 totaled 6.8 million tons, impressive for an island nation but dwarfed by American production of 82.8 million tons, a ratio of more than 12 to 1. Japanese shipyard capacity across all naval and merchant construction totaled roughly 1 million tons annually under ideal conditions that never existed in wartime. American shipyard capacity exceeded 15 million tons and expanded rapidly as new yards were built and existing facilities enlarged. The ratio was 15 to 1, and it widened as the war progressed because American yards grew while Japanese yards shrank under bombing and resource starvation. American yards expanded by adding new building ways, hiring women and minorities who had been excluded from shipyard work, and implementing prefabrication techniques that reduced a Liberty ship's construction time from 230 days to 42 days on average, with one ship famously completed in just 4.5 days as a publicity demonstration showing what motivated workers using proper techniques could achieve. Japanese yards, meanwhile, were overwhelmed with repair work, constantly bombed after 1944, and starved of steel, copper, aluminum, and skilled labor drafted into the army to replace casualties in China and the Pacific. Yokosuka Arsenal, which had built Shikoku in 44 months during peacetime, could barely maintain existing ships by 1945, much less build new ones. The yard was bombed repeatedly by B-29s attacking from the Marianas after November 1944, with raids destroying cranes, workshops, and administrative buildings while killing skilled workers who could not be replaced. Material allocation prioritized immediate combat needs over long-term construction, so steel went to building kamikaze aircraft and suicide boats rather than carriers that would take years to complete. Copper and aluminum were hoarded for aircraft production, leaving shipyards unable to obtain wiring and structural components essential for carrier construction. The few carriers still under construction in 1945 were suspended at various stages of incompletion, their hulls cannibalized for parts to repair damaged ships returning from combat. Japan's carrier construction program collapsed not because Japanese engineers were incompetent or Japanese workers lazy, but because the entire premise was flawed from the start. The premise was that carriers could be built fast enough to replace battle losses while simultaneously conducting offensive operations against an enemy with 10 times the industrial base and unlimited access to resources Japan lacked. It could not be done. The mathematics were unforgiving and immutable. At midway on the 4th of June, 1942, Japan lost 4 fleet carriers, Akagi, Kaga, SRY, and Hyori, in one afternoon of combat. Replacing them required at minimum 2 years even under emergency conditions assuming materials and labor were available, which increasingly they were not. During those 2 years, America added 14 Essex-class fleet carriers, 9 Independence-class light carriers converted from cruiser hulls, and 24 escort carriers built on merchant hulls to the Pacific Fleet. The imbalance widened from rough parity in June 1942 to overwhelming American superiority by June 1944 when the Battle of the Philippine Sea saw American carrier aircraft destroying Japanese carrier aviation in what American pilots called the Great Marianas Turkey Shoot. No amount of Japanese construction could close that gap because the gap was not fundamentally about ship construction rates but about industrial capacity, resource availability, and strategic depth that Japan simply did not possess and could not create. Consider the resources required to build a single fleet carrier in 1942. Steel, 25,000 to 30,000 tons for Japanese carriers depending on protection levels and equipment fit, slightly more for American designs that incorporated heavier armor and more extensive subdivision. Copper, 500 tons for electrical wiring running through every compartment, powering everything from main distribution panels to individual light bulbs. Aluminum, 1,000 tons for aircraft handling equipment, boat davits, and lightweight structure where weight savings justified the expense of a metal more costly than steel. Oil, 10,000 tons for machinery lubrication and fuel storage tanks, plus another 1,000 tons of specialized lubricants for bearings, gears, and hydraulic systems. Rubber, 50 tons for gaskets, hoses, insulation, and countless small components that sealed joints, carried fluids, and prevented vibration. Each carrier also required for massive steam turbines weighing 100 tons apiece, 8 boilers weighing 50 tons each, 2 or for propeller shafts weighing 30 tons each and measuring over 100 meters long, 120 miles of electrical cable in sizes from hair-thin control wiring to arm-thick power cables, 3 million rivets before welding became standard, or 1 million rivets plus thousands of feet of welded seam for hybrid construction, armor plate rolled to precise thicknesses and hardened through heat treatment processes requiring specialized furnaces and skilled metallurgists, optical rangefinders using precision ground lenses that could only be produced by a handful of manufacturers worldwide, radar systems after 1942 using vacuum tubes and components that required dedicated factories, radio equipment including transmitters, receivers, encryption machines, and antenna systems, navigational equipment including gyro compasses accurate to fractions of a degree and chronometers maintaining time to within seconds over weeks at sea, medical facilities with surgical suites, X-ray machines, dental chairs, and pharmacies stocked with medications for hundreds of crew, galleys capable of preparing 3 meals daily for over 1,600 men using steam kettles, ovens, refrigerators, and dishwashers, freshwater distillation plants turning seawater into drinking water at rates exceeding 100 tons per day, and the labor of thousands of workers for months of round-the-clock effort coordinated across dozens of specialized trades and hundreds of subcontractors. Japan's entire annual steel production in 1941 could theoretically build perhaps 12 fleet carriers if no steel was diverted to merchant ships, destroyers, cruisers, battleships, submarines, tanks, artillery, railroad rails, or the 1,000 other demands of total war and modern industrial economy. In practice, carrier construction consumed only a fraction of available steel because other programs had equal or higher priority. The combined fleet required destroyers to screen carriers, cruisers to provide gunnery support, battleships to engage enemy battle lines, submarines to interdict supply lines, and tankers to transport fuel from the Dutch East Indies and Borneo to fleet bases in Japan. The army required steel for tanks, artillery, trucks, railroad equipment, and fortifications across an empire spanning from Burma to New Guinea. Civilian economy required steel for factory construction, bridge repairs, and industrial expansion necessary to support war production. Available tonnage had to be divided among competing demands, with carrier construction receiving perhaps 10% of total steel allocation under the most optimistic circumstances. 10% of 6.8 million tons was 680,000 tons annually, theoretically sufficient for 27 carriers per year at 25,000 tons each, but practically sufficient for perhaps 3 carriers after accounting for waste, rework, defective material, and the reality that not all steel was suitable for shipbuilding even if allocated to that purpose. America, by comparison, could devote 10% of its 82.8 million ton steel production to carrier construction and build 330 carriers annually at 25,000 tons each. Even allocating just 1% produced 33 carriers per year, more than Japan could build in a decade. The disparity was not about efficiency or skill. It was about fundamental resource availability that no amount of efficiency could overcome. The pilot shortage was equally insurmountable and more immediately critical than shipbuilding capacity. Training a carrier pilot required 2 years minimum under Japanese pre-war standards, 6 months basic flight training learning to take off, land, and control an aircraft in normal conditions, 6 months advanced training mastering aerobatics, gunnery, navigation, and formation flying, 6 months carrier qualification practicing deck landings and catapult launches under progressively more difficult conditions, and 6-month squadron integration learning coordinated attacks and defensive tactics. With the unit the pilot would join in combat. Japan began the Pacific War with approximately 3,500 trained naval aviators, the product of a brutal selection process that accepted only the best physical specimens and most motivated candidates from each year's graduating class of basic flight students and washed out everyone else. The training program deliberately emphasized quality over quantity, accepting high washout rates to ensure every graduate met rigorous standards for skill, discipline, and combat effectiveness. These pilots were superbly trained, capable of feats like night carrier landings that American pilots would not attempt until late 1943, when radar and improved deck lighting made the Evolution safer, able to navigate hundreds of miles over open ocean without radio aids or even reliable compasses in some aircraft types, and drilled in coordinated squadron attacks that maximized striking power while minimizing vulnerability to enemy defenses. American pilot training in 1941 was less selective but more scalable, reflecting different philosophical approaches to training influenced by different strategic situations. America possessed larger population from which to draw candidates, higher educational levels providing larger pool of potential pilots who could master technical subjects required for aviation, and industrial capacity to produce training aircraft, fuel, and facilities in quantities Japan could never match. American training emphasized producing adequate pilots in large numbers rather than excellent pilots in small numbers, accepting that many graduates would learn remaining necessary skills in combat with their squadrons rather than in training command. This approach was heresy to Japanese instructors who believed that poorly trained pilots were useless burdens who would die quickly and accomplish nothing, but it reflected American understanding that numerical superiority could compensate for individual skill deficiencies and that losses could be replaced continuously rather than accepted as irreplaceable. By 1943, American flight schools were graduating 10,000 pilots every 6 months, overwhelming Japanese defenses through sheer numerical superiority even when individual Japanese pilots possessed superior skill based on longer training and more stringent selection. Japanese air groups were being attrited faster than replacements could be trained using pre-war standards, forcing steady relaxation of training requirements to maintain numerical strength. Japan attempted to accelerate pilot training after Midway losses forced recognition that pre-war training tempo could not replace combat attrition, reducing the curriculum from 24 months to 18 months in 1943, then to 12 months in 1944. And finally to 6 months in 1945 as desperation mounted and American advances captured training bases, forcing consolidation of programs into fewer facilities with less fuel available for practice flights. The result was novice pilots who died in their first combat mission, unable to find their carriers after a strike because navigation training had been truncated, unable to evade enemy fire because aerobatic training had been reduced, unable to land safely on a pitching deck at night or even in daytime rough weather because carrier qualification had been compressed to minimum proficiency rather than thorough competence. New carriers sat in harbor for lack of trained crews to operate them. Aircraft sat unfueled for lack of gasoline to fly them. The construction time that mattered was not how fast you could build the ship but how fast you could build the complete system, ship plus aircraft plus pilots plus fuel plus escorts plus ammunition plus doctrine plus experience plus institutional knowledge that could only be gained through years of practice. Japanese carrier doctrine compounded the construction and personnel problems by emphasizing tactics that maximized risk while producing diminishing returns as the war progressed. Pre-war training stressed massed carrier strikes, concentrating 4 to 6 carriers in a single task force for overwhelming local superiority at the point of attack. This doctrine reflected Japanese naval philosophy inherited from Admiral T.G.'s victory at Tsushima in 1905, where concentration of force at the decisive point produced overwhelming victory, and it was sound theory when applied by skilled forces against inferior opponents in situations where the decisive battle could be identified and forced. Pearl Harbor demonstrated the doctrine's potential when 6 Japanese carriers achieved complete tactical surprise and devastated the American battle line. But the doctrine also maximized vulnerability by concentrating irreplaceable assets in a small area where a single enemy counterattack could destroy multiple carriers simultaneously. Midway proved this vulnerability when American dive bombers caught for Japanese carriers refueling and rearming aircraft on deck, destroying all for in minutes through a combination of luck, skill, and Japanese tactical errors that massed their carriers so tightly that a single attack could hit multiple ships. Losing 4 carriers at Midway eliminated not just for ships but the institutional knowledge of their entire air groups numbering approximately 250 aircraft and 500 pilots plus maintenance crews, flight deck officers, air operations personnel, and the admirals who commanded them. The loss was not merely numerical but organizational, destroying the only force in existence that had practiced coordinated 6-carrier operations for years and proven its capability at Pearl Harbor. Subsequent attempts to reconstitute multi-carrier strike forces failed to achieve the same level of coordination because the experienced cadre who could train new pilots and integrate new ships no longer existed in sufficient numbers. American doctrine, influenced by the same Midway battle, deliberately distributed carriers in task groups of 2 or 3 ships with heavy surface escorts, ensuring that a single disastrous engagement could not cripple the entire force and allowing continuation of operations even after severe losses. When USS Yorktown was sunk at Midway, USS Enterprise and USS Hornet survived to continue fighting and serve as platforms for rebuilding carrier aviation. When USS Hornet was sunk at Santa Cruz in October 1942, USS Enterprise survived despite heavy damage to fight again at Guadalcanal in critical night actions that prevented Japanese forces from reinforcing their garrison. When USS Princeton was sunk at Leyte Gulf in October 1944, 15 other American carriers continued operations unaffected by the loss. American carriers could be lost without losing the war. Japanese carriers could not because Japan lacked sufficient industrial capacity to replace them and sufficient training capacity to replace their air groups simultaneously. The Shinano exemplified Japanese desperation in the war's latter stages when rational planning had given way to grasping at technological solutions for strategic problems. She was laid down on the 4th of May, 1940 as the 3rd Yamato-class super battleship, hull number 110, a 72,000-ton monster that would have been the most powerful surface combatant afloat when completed, mounting 9 18.1-inch guns in 3 triple turrets capable of firing 1,460 kilogram shells to ranges exceeding 40,000 meters. After Midway demonstrated that carriers not battleships would decide the Pacific War, she was converted to an aircraft carrier while still on the building way at Yokosuka Arsenal, a decision made in July 1942 that consumed 3 years of construction effort and produced a vessel of questionable military utility. The conversion required scrapping the partially completed superstructure and armament, redesigning the hull structure to accommodate hangar decks and elevators, and fabricating new components for systems that had not been part of the original battleship design. At 62,000 tons standard displacement and 72,000 tons fully loaded, she became the largest carrier ever built until USS Forrestal in 1955, a dubious distinction given her actual capabilities. Her armored flight deck was 256 meters long and 40 meters wide, among the largest carrier decks in the world, but she carried just 47 aircraft operationally with room for perhaps 60 in emergency overload conditions. The aircraft-to-tonnage ratio was pathetic, approximately 750 tons of ship per aircraft compared to 400 tons per aircraft for Essex class and 360 tons per aircraft for Shikoku, reflecting her design as a support carrier for frontline fleet carriers that would strike enemy targets while Shinano provided reserve aircraft to replace losses. This concept might have been useful in 1942 when Japan possessed sufficient fleet carriers to benefit from dedicated support ships, but by 1944 when Shinano commissioned the frontline carriers no longer existed and the concept had become irrelevant. Her speed was 27 knots maximum, achieved by retaining the Yamato-class machinery plant originally designed to drive a much heavier battleship to higher speeds, but 27 knots was too slow to operate with fleet carriers rated at 33 knots and barely faster than the merchant convoys she might have escorted if assigned to that role instead of fleet operations. She was commissioned on the 19th of November, 1944 at Yokosuka after delays caused by bombing raids, material shortages, and design changes implemented during construction, and sunk 10 days later by USS Archerfish while transiting from Yokosuka to Kure to complete fitting out and embark her air group. The submarine attack occurred on the 29th of November, 1944 in calm seas with excellent visibility, conditions that should have favored the target but instead allowed the submarine to track her for hours before achieving ideal attack position. Archerfish fired 6 torpedoes from a range of just 1,400 meters, a point-blank shot by submarine standards that reflected either remarkable skill by the American submarine commander or remarkable incompetence by Japanese escorts who failed to detect a submarine tracking them for hours. 4 torpedoes hit Shinano's starboard side, flooding boiler rooms and adjacent compartments through poorly fitted watertight doors and hull penetrations that had not been properly sealed during hasty fitting out. The ship initially maintained way and course, her massive size seemingly able to absorb punishment that would have sunk smaller vessels immediately, but progressive flooding gradually overwhelmed damage control efforts by untrained crews who did not know the ship's layout or damage control systems that had not been properly tested before departure. 7 hours after the attack, Shinano capsized and sank with loss of 1,435 of her 2,515 crew, the shortest operational career of any fleet carrier in history and a monument to the waste of resources that characterized Japanese naval policy in the war's final years. Her construction consumed steel that could have built 3 Unrei-class light carriers or 6 destroyers. Her machinery plant could have powered 2 fleet carriers. Her construction labor could have repaired a dozen damaged warships or built 20 escort vessels. Her crew could have manned 4 destroyers or 2 cruisers. Her loss proved that size without competence was suicide, that rushing incomplete ships to sea produced catastrophe rather than capability, and that Japan's situation by late 1944 was so desperate that even obviously futile gestures, like commissioning inadequately prepared ships, seemed preferable to acknowledging that the war was lost and further sacrifice pointless. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.